Welcome, everyone, and thank you for joining us for today's webinar, Optimize Your Supply Chain with Knowledge Graphs. My name is Amanda, and I am part of the virtual events team here at Neo4j. And I'm thrilled to be joined by Michael Moore, Senior Director, Strategy and Innovation at Neo4j. We are super excited to have you all with us today. Just a quick note about questions before we get started. We invite you to submit any questions you have throughout the session using the Questions tab located at the top of your screen. We'll answer as many questions as possible at the end of today's presentation, and if we don't get to them all, someone on the Neo4j events team will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. So with that, I'll go ahead and hand it over to Michael.
Hello, everyone. Thank you for spending some time with us to learn a little bit more about what you can do with knowledge graphs and optimizing your supply chain. I'm Michael Moore, and let's get into it. So if you think about what drives your business processes, right? You're running a global supply chain. You've got a lot of dependencies, and what we like to focus on at Neo4j is while it's true you have a lot of facts, a lot of individual entities that you're trying to manage, your ability to actually understand the state of your supply chain really rests on your ability to understand the relationships and the interactions between all of the entities that are involved in your supply chain. And so, for example, you've got in your organization, you've got employees, you've got customers, you've got parts, products. You're operating various services across different regions. Some of your capital investments will include things like plants and warehouses. You'll have suppliers and distributors. Obviously, you've got competitors. You'll probably be working through some kind of partner ecosystem. And of course, you're going to be operating in some kind of a regulatory environment. And so your ability to manage your supply chain, optimize it, understand its condition, its dependencies, its vulnerabilities, and resiliency all depends on knowing how these different types of entities are connected. And often you need to know those connections and those statuses in real time. When you look at large systems, like for example, this is the Port of Oakland in California. This is in fact a graph. And like the structure that we just showed you on the previous slide, when I look at this, I see an intensely hierarchical system of dynamic components. We've got ships, we have containers, we've got packages inside those containers, obviously, millions of them, right? And all of them have suppliers, they have buyers, they have destinations, there's SLA expectations, there's paperwork and documentation associated with all of these. And then look at the logistics. All of these containers are going to get offloaded on either trains or trucks. And it's a complete network of goods, coming in, moving across, an entire continent. And guess what? In a week or so, it's going to be a whole different ship, right? And so graphs are very, very good at representing these kinds of complex systems, because you have the ability to connect all of the elements, and you're not mathematically limited by how complex those connections can be. This is one of the reasons why analysts are so excited about graphs and graph technology. And Gartner recently stated that they feel that 80% of data and analytics innovations are going to be driven by graph technologies. So what does it mean when we're talking about a graph? We're not talking about charts like pie charts or XY plots or anything like that. A graph is a data representation where you basically are looking at two types of data. You're looking at what you call your entities, and so we call those nodes in our property graph model. And so, for example, on this diagram, I have suppliers, and I have products, and I have parts, and I have buyers, right? Now, the other major type of data that we have in a graph are the relationships. And so the relationships here that we're showing on this one is, for example, a supplier produces a product, right? A product has a part has a subpart. And you can actually see over here, we've got this little curly Q relationship here. That means that this could be recursive. And so basically you could have subparts that have subparts that have subparts and so on to any depth that you need in the graph. And you also have things, like buyers purchasing parts. And you can start to see like the graph holds not only complex information about things like bills of material, but it's also handling things like transactions. And so typically when we think about a graph, we think about these nodes. The nodes can have data on them represented as key value pairs. The relationships also can have data on them. And what makes a graph really special is all of these relationships. And the relationships will have semantics, which means that they have a name. They'll have a directionality. So for example, that buyer purchases a product, and you can see that the relationship goes from the buyer to the product. And this makes sense, right? Because products don't buy buyers, right? They don't purchase buyers. And so the relationships give you a really crisp semantics for understanding exactly how your data is related. And you can represent that very elegantly. The other thing that's interesting about relationships, the way that we depict them, is each one has an ID. It's a first-class data citizen. It's stored on disk and in memory. And in fact, all of the logical possible relationships in a graph are computed and created when you load data into the system. And so then what happens is at scale, you end up with a really large connected fabric of data that is completely networked, and you can explore that to any dimension or any depth in that graph. And so it's incredibly powerful, and it gets over the hurdles of many of the limitations that are associated with legacy SQL and NoSQL systems when it comes to analyzing large, complex data sets. Another thing that makes graphs quite interesting is it isn't as if we didn't understand the importance of the graph data model, 20 years ago or 40 years ago. But the problem is that the cost of computing was so high that you couldn't actually create all of these relationships. And so, for example, when Oracle was first put together in the late 1970s, it would have cost you $10,000 for a megabyte of RAM. And now both compute and memory are so cheap, you can ask yourself, well, why wouldn't we store all of the relationships directly, right? And of course, SQL systems don't do this, nor do NoSQL systems, right? They both basically have keys that indicate the presence of a relationship, but in order to work with that relationship, it has to be computed at runtime, which puts a lot of overhead on the queries and passes on that workload to essentially every single user. And this is why these systems really can't handle the kinds of relationships that we're talking about. Another aspect of this is that one way you can think about graphs is that we're actually operating up at that conceptual data model level. And we don't have to do things like build a logical data model or build a physical data model in order to work with the data. We can actually depict the business as a graph, and we store the data as a graph, we query the data as a graph, and that way we avoid a lot of technical debt associated with SQL and NoSQL systems. One expression of this is exactly how you can see in how the graphs are actually laid out. So on the left, for example, this is the ER diagram for Oracle's supply chain module. And you can see all of the complexity associated with this. You've got join tables, you've got a lot of constructs in order to be able to handle at least even a partial view of a global supply chain. In the graph model, you can see that we can represent all of the same entities, but you end up with a much more elegant structure. And this structure is something that you can go talk to a business stakeholder, and you can say, do we understand this correctly? Are we missing anything? Do we have all the right relationships? And more often than not, that business stakeholder will be able to look exactly at what you've designed and say, you know what, you've got it correct, or there's something missing here. And, you can immediately just go ahead and add that in. So very handy, low complexity, high fidelity. Another aspect of graphs is that because all of the relationships are first-class citizens, they're stored on disk, they're stored in memory, it means that when we run a query, we don't actually have to do anything other than land on the starting point of the query, and then the query planner will fan out a cursor and explore all the connected data locally around that starting point. And the huge benefit associated with that is that while other systems always have to consult global indexes and things like that in order to process a query, in a Neo4j graph, We only use indexes to find the starting point of a query, and then all of the data discovery is done locally, which then means that as that graph gets larger and larger and larger, you don't have a rapid degradation in query performance, which is essentially inescapable in relational and NoSQL systems. And so we regularly can take queries that aren't performing in legacy systems, you move that data into the graph, and you'll see a giant improvement in performance, especially as you try to do more complex analyses. So what is Neo4j? So Neo4j is a pretty remarkable system. So we can handle all three major workloads in data management. So we can handle OLTP transactional workloads, OLAP analytical workloads, and we also have built-in machine learning algorithms that allow you to analyze the graph at scale. The architecture that we use for Neo4j is what's known as a native graph architecture. So when we write data to disk, that data is laid out in the form of a graph. It's stored in memory as a graph. Our query planners operate off of graph algebra, and our language that you use to write queries essentially represents your declarations in the form of a graph. We support all manner of data shapes and data types. We can handle, as I mentioned, these hybrid workloads that are both, OLTP, OLAP, and machine learning. We have a giant tool set for all, and we support all common programming languages. We have drivers and connectors for, all major data management components in an enterprise ecosystem. As I mentioned, we have graph data science. We'll take a look at that in a little bit more depth in just a bit. And we have a really large community of graph developers, well over 250,000 globally, and that's growing at about 80% year over year. We put a lot of effort in the system to make it enterprise ready from a trust and security perspective. We're SOC compliant. We run on all three cloud providers, Azure, Google, and AWS. And then, of course, you can also run on-prem and bare metal. And we've got lots of great capabilities around scalability, clustering, et cetera, to manage whatever the workload is that you may have. So what makes graphs powerful is that they naturally handle complex data. And so if we take a look at the kinds of complexity that graphs do a really good job at. So, it's not unusual that you have problems of analyzing data that you might call wide data. So I have a single object, so maybe it's a customer, maybe it's an asset. And in order to understand that in its context, I need to join that with a large number of other tables or, data sets. In a graph, you can do that very naturally. Graphs also handle complex data where there's lots of many-to-many relationships across data points. And then, as I mentioned earlier, anything that is hierarchical or recursive or requires, deep pathing, like routing or bills of material, et cetera, all of that kind of data can be easily represented in a graph and easily and quickly analyzed. And then at an enterprise level, we often see graphs being deployed to do things like unify and mobilize data, legacy data across, say, separated systems, or even when there's been a lot of work around centralizing data in data warehouses and data lakes, we still see customers moving that data up into a graph to basically unify and conform that data and make it usable to the business. And then finally, graphs are excellent at identifying hidden data. And so by hidden data, I mean there's latent information in the graph, and you can discover that through inferential analytics. And so, for example, in this simple scenario, if A connects to C and A also connects to E, we might be able to predict that, in fact, there's some kind of linkage or dependency between C and E. And also we have, capabilities around looking at, mathematical similarity between nodes and vector representations of data. And all of this becomes extremely powerful in the world of machine reasoning and Gen AI. So turning to supply chain, what are some of the issues associated with analytics in the world of supply chains? So some of the key areas where organizations have challenges are in doing things like demand shaping, inventory positioning, being able to provide high quality fulfillment predictably, and then also in the area of sustainability. And the biggest obstacle to being able to perform these kinds of capabilities at scale is usually end-to-end supply chain visibility. And this is what your graph will get you, is the ability to look at your supply chain from an end-to-end perspective and be able to handle some of these concerns. I want to focus on sustainability here for just a second. In the next several years, there's going to be quite a lot of focus on what are known as the Scope 3 reporting requirements. And what Scope 3 does is it sets out standards for doing carbon emissions reporting across the entire value chain. And these requirements, reporting requirements, are going to be first estimates are due in February of 2025, which is really just right around the corner. And what's quite interesting about the Scope 3 requirements is that it requires that you have an understanding of all of the emissions associated with your upstream and your downstream supply chain and distribution. And for most organizations, 90% of their emissions are coming from their supply chains. The data collection that's associated with this is quite formidable. It requires upstream and downstream transportation data. It requires that you understand the mode of transportation, that you understand the raw materials and energy consumption from all of your suppliers. And then when you get that figured out, then you're going to add it to your existing Scope 1 and Scope 2 estimates for the total carbon estimate for your organization. And digging into this, what we see is a lot of calculation complexity and a lot of complexity associated with companies, tier 1 and tier 2, tier 3, etc., suppliers. And it's very hard for us to imagine how an organization would even get a handle on this unless they were managing their data in a graph. And so just to kind of round this out, so we believe that supply chains are natural graphs, and the ability to analyze your supply chain and achieve things like global supply chain visibility, be able to do dynamic routing and logistics, manage bills of material, understand the resiliency of your supply chain, and as I mentioned, provide meaningful estimates of your carbon footprint. All of these analyses are best conducted in a graph, and this is really just an expression of the complexity and the linkages that are naturally inherent in a global supply chain. We have a number of customers that are building out supply chain graphs. Some notable ones include the U.S. Army, which is running a really large Neo4j graph that has all of the suppliers for all of the material that the Army puts into the field globally. And they're using this for doing analytics and simulations. Caterpillar uses Neo4j to do root cause analysis around all of its heavy equipment, and they are basically combining NLP with graph to understand major failure modes and anticipate maintenance that they'll need to perform depending on how that individual asset has been deployed and maintained over time. Orbit MI is a marine routing company, and they were able to move what was a formerly relatively manual routing process into Neo4j, and they're able to compute global sub-second routes, and as an outcome of that, they were able to reduce their fuel costs, which then reduced their carbon footprint, and they were able to pass those savings on to their customers, which made them more competitive. So what are some of the tools that you use when you go down an optimization path with Neo4j? So there's obviously the Neo4j graph database. So this is where you would house the digital twin of your supply chain. You would also be using Neo4j's graph data science library for doing inference and predictions. And then you can use tools like Neo4j Bloom to do visualization and investigation of aspects of your graph. So the starting point for all of this is recognizing that you can use the graph to basically make a digital twin of your supply chain. And where you start on this is really it's a matter of necessity and preference. But you can think about it as, maybe you want to have a global network view, or maybe you want to focus on a particular site and look at things like manufacturing lines and quality control issues and dwell times for specific things. We see customers doing both of those, and then as their graphs mature, oftentimes we see linkages between these high-level views and then these more detailed views. The typical approach is you would build out that supply chain knowledge graph by identifying, what are, if you have industry ontologies and taxonomies that you want to adhere to, you would bring all of that terminology into the graph. You would resolve the various entities that are interacting, like in that very first slide that I showed, and you'd get data sets representing the interactions of those entities. Most of these graphs will have some layer of operational transactions. And so these could be things like purchase orders, they could be waybills, they could even be GPS signals. They're giving location data of assets that are moving around the globe. And they could be, IoT based alerts, maybe around manufacturing or a smart factory type scenario. So you could have real-time context. And then finally, almost all of these graphs will have a lot of work happening in the area of graph inference and the application of algorithms for driving that graph-based analytics. And so you'll be doing things like community detection, running algorithms to identify points of failure, bottlenecks, shortest paths, etc. Some of the key algorithms that we see customers applying when they're analyzing their supply chain digital twin. Pathfinding is a big one. And so this is usually the problem of figuring out what is the shortest route between 2 points and optimizing against some cost factor. And so that could be time, it could be physical distance, it could be fuel cost, etc. And then also proposing alternate routes in case there's some kind of a disruption. Centrality is an algorithm that allows you to understand how connected a particular object is or a particular entity. And so you could think about something like a distribution hub, right? And you run these kinds of algorithms and it'll quickly identify which are the most important distribution hubs overall. And it'll show how they're connected to other hubs. And it'll give you a view of if that distribution hub was to, say, go down, where else could you run your distribution through? Node similarity is another important algorithm that's used to identify things like replacements. And so this can be done at a couple of different levels. It could be done at, say, a facilities level, depending on how that's characterized, or you can do it at a, say, a bill of materials level where you're looking for parts that have, similar fit and function. This is used to do things like understand inventory shortfalls or maybe logistics disruptions and how you'd handle those. And then finally, we provide the ability to embed pretty much any manner of data as a vector in the Neo4j database, which then allows you to do things like semantic search and power Gen AI type experiences. So I'm going to show a couple of demos as part of this. And the first one that I'm going to show is just a simple demo on how our graph data science package functions. And what we're going to do is we're going to explore what's known as the North American Rail Network data set. This is distributed by the DOT, and it covers all of the rail lines in North America, and it has about 500,000 miles of track represented. And so the way that we model this is actually pretty simple. So we have yards, and yards connect to track, and the track has various characteristics. And of course, then track connects to other track, and you build up the whole network that way. Now, the problem that we're going to try to solve is a routing problem for double stack rail cars. A double stack rail car is one where I might have one or two containers, one on top of each other. And if you think about this whole rail network, it becomes very quickly obvious that there's going to be sections of the rail network where you can't actually run one of these tall trains. And so to handle that, what we're going to do is we project from the data graph that we've built, and we create two projections: a main network that has the entire network and can handle standard rail cars of standard height. And then within that network, there's a subgraph or a subnetwork that is guaranteed to not have any low bridges and tunnels, which would obviously, not handle the tall train car, right? You'd have some kind of an accident. What does this actually look like from a code perspective? It's actually very simple. So once our graph is built, we just call a projection procedure, and it goes and creates this view of the graph. And so the two views that we're creating are the main lines network, and then the double stack network. And the property that we want to optimize for is miles, and we want to minimize that when we run our algorithms. So having these two projections up in memory then allows us to pick a route. We pick which of the projections we want to do our pathfinding on, and then you can see here where we ask the algorithm to minimize for the aggregate value of miles, and it will search the entire network and come up with the shortest path. And so here's a screenshot of that. And this is the double stack network. So let's go look at this live. And I'm going to bail out of this for 1 second. And we're going to take a quick look at the database. And so this is this database of track. And you can see here I have yards, and I have track, and I have a couple of different kinds of relationships, right? So I have relationships built that represent track that can handle double stack trains, and track that handles, standard trains. If I run our query here, we can see what this looks like. Okay, and so here is our environment, and this is the query that we ran. So I'm just telling Neo4j, give me some paths starting at a yard down in Louisiana, and I want you to go out 4 hops and show me what connects to what. And so here is the Gentilly yard. Here's another yard that's called France. And you can see here that the graph is connecting all of these things. And so, of course, if I'm a dispatcher, I can run a train from this yard to this yard along these tracks. You'll notice here that I can put data on all of the relationships. And so this is some of the data. And you can see here that this particular segment of track is about 1/10 of a mile. And, it's got a lot of characteristics about it. And these are the nodes, for example, and you can see that I've got these geographically located and named and so forth. If I want to see the projections, we can just call, and we've already run that code to do the projections. And so you can see here that I've got a projection for the double stack network, which is a subnetwork. And it's got in it about 250,000 nodes, and it's got about 150,000 paths on that. And then I've also got the main lines network, which is quite a bit bigger. Again, about 250,000 nodes, but now you can see about 500,000 track segments in it. So let's see, what does this actually look like? And so this is a tool called Neo4j, and Neo4j is a Neo4j Labs project, and it allows you to basically create a dashboard and work with your graph interactively. And so I can pick different locations, and so I've picked a location from Detroit down to Gentilly here in Louisiana, and I've asked it to say, find the shortest path through the entire North American rail network graph that connects these 2 points. And so there's our answer. It's about 988 miles. Now, if my dispatcher says, you know what, that's actually a double stack train, and now we can run that. And there you have the answer. And you can see that compared to the prior route, we've had to avoid the states of Kentucky and Tennessee, presumably because somewhere along those routes are some low tunnels or bridges. And we can also do things like look at ownership of the track across this route and so forth. The key thing that I want to show you, though, is let's take a look at what's actually under the hood here. And if I go look at this, you can actually see that we're running this whole analysis with only 3 lines of code. And that's pretty cool. So that's just a very quick demo on pathfinding. And so this could be used for routing or across a global network. And so now let's go take a look at another demo. And so this one is some work that we did with Google around basically supply chain analytics from a manufacturing order perspective. And what Google has done is they have created a set of interfaces that can unload data from say, SAP and Oracle systems. They put that into BigQuery. They have an L2 model of the schemas that they've pulled together. And then we've taken that and turned that into a graph model, and we can bring the data into Neo4j and then do various kinds of analytics. And so let's take a quick look at this schema. You can see here we've got things like plants and customers and suppliers. There's manufacturing orders. There's inventory. There's the actual bill of materials that then comprise the product, etc. And so we'll take a quick look at this one. And so in this model, what we're doing is we're basically analyzing inventory shortfall. And I'm going to zoom out here. Let me just refresh this 1 second. There we go. That looks a little better. And so you can see here, of the manufacturing orders that I have, of the manufacturing orders that I have, I've got 60 or so that I can't fulfill. And so if I drilled into one of these, we can go look at this graph, and this is this order, and you can see that I've got 4 levels of hierarchy here. So this is sort of a simplified bill of materials. In the real bill of materials, this could go down to 20 or 30 different levels. I see that this particular order is in a shortfall status. So, and I can actually flip this analysis, and I could say, and I can learn what parts are in a shortfall state that are actually causing me to not be able to deliver this order. And so I'm walking the graph down 4 levels, and I can identify that one of the items is this thing called a 9-bit parity generator that's down at the L4 level. So what can we do with this kinds of information? So one of the things that we can do is we can go investigate these part shortages across our supply chain. And so if I open up this particular manufacturing order and I start working my way through its bill of materials, you can see that I'm short 26 items, finished items. And I can see also here that the graph is telling me that this sensor pressure is an issue, and I keep drilling into this, and then I can see that, yes, in fact, here is this thing that's called a parity generator, and I'm short 28 of these things, and this is what's going to cause me to not be able to deliver on this particular manufacturing order. And so we've walked from the L1 part all the way down to the L4. Now, if we click on this, we can do a really interesting analysis. So obviously, this part is essential to this particular order. But guess what? We can also walk from that leaf level element in the graph all the way up to other orders that shortage is affecting. And now I discover that in fact, there's about 10 other orders that aren't going to be able to be delivered because of a shortfall of this one part. So that's an example of a graph analysis where we've walked down to something and we've walked up into graphs of other bills of material or other orders that are in our manufacturing queue. I can also do things like run algorithms like centrality and look for things like part contention. And so again, I can take a look at all of the different parts that are in a shortfall status. I could actually calculate what would be a safety stock order that I would need to rectify that. And what we're doing here is we're actually creating an aggregate risk score that's based on things like where is the facility located, how many orders are there that require this part, and how much contention is there around this part in general. And so, for example, we can take this information, we can say that if we order an additional set of parts, we can then solve this problem. And so if I go ahead and order those, now you can see I've lowered my risk score and I'm going to be able to deliver on that particular item. If we go out to a global level, we can actually map this. And so if I look at that one order that we were looking at earlier, now I'm looking at the global supply chain of this particular manufacturing order. You can see all the facilities that are involved here. You can see that we have a shortfall status associated with this part. And one of the things that we can do is, because we know we've run similarity analyses, we can also do things like determine right out of the gate what would be some alternate parts that would have the same fitment and function, and where are those being manufactured. And so now you can see here, I've got some choices about where I could actually find replacement parts around the world. And often, in order to do this, you actually have to be able to unify the data, because sometimes these suppliers will call the same thing by a different name. And so again, you can do that kind of work in the graph. And so now if I go look at this, I can see here, I've got in these golden lines, this is the supply chain for these alternate parts. Some other things you can do is you can bring in external data. And so, for example, if I go down here into southern China, I can look at some nearby issues. And if I was to pull up some of these, you can see that I've enriched this graph with news articles on the condition of the economy and logistics in this particular region. And I might factor that into my risk calculations and my delivery times for components where I have a dependency on this region. And then finally, we can drill into some specifics around these bills of material and their contention across my manufacturing orders. And so this is a tool called Bloom, and Bloom has a number of uses. One of the ones that we like a lot is that you can actually pre-program it with queries that then an analyst can use. And so, for example, let's go ahead and I can drill into this query here, and you can see here that there's a query, and then I can go ahead and just access this query by using a simple search phrase. And so in this environment, we can spot up to 10,000 nodes. And so let's run this query, and we'll interrogate the graph. And There we go. Okay, and so now it's rendered all of these objects. And so what we're looking at here, if I zoom in a bit, is these are parts, and I'm showing these are the L1 parts and some of the parts that are required to complete these. And what we can do is we can actually style these by some attributes that have already been created. So for example, I told you that we use centrality. And so let's look at the betweenness score for these, and we'll do a range, and we'll apply the color here. And now you can see we've identified which parts are likely to have the most contention because they're actually being used by a number of different products that my organization is manufacturing. And so this is just another example of a very fast type of analysis. And so then these parts I might really want to be focusing on for building out safety stocks around, because they're going to be consumed by a number of other products. All right, and so that is it for the demos. And let me get back to our slideshow here. And so just want to leave you with the point that the modern supply chain is in fact a knowledge graph. And as you think about all of the different dynamics associated with this running a global supply chain, your ability to analyze it, your ability to make it resilient, your ability to do things like report on sustainability and be able to do fulfillment, inventory positioning, etc. All of those kinds of analytics can be done in a knowledge graph, and they can be done much faster and much more powerfully with a knowledge graph. Thank you.
All right, thank you, Michael, so much for a great presentation, as well as the demos. It looks like we do have some time for a few questions today. So first, I did want to remind the audience, if they'd like to submit a question, they can do so by typing it into the questions tab at the top of your screen. We did have a few questions come in already, so let's go ahead and get started with those. This first question, this person wants to ask, how large of a graph can I build?
You can build graphs out to amazing sizes. So Neo4j scales very well, and we have customers that are running graphs that have billions of nodes and tens of billions of relationships in them.
Awesome, thank you. Okay, moving on. The next question, this person asks, can I load industry standard ontologies, taxonomies into Neo4j?
Yes, absolutely. Yeah. So we have a package called Neo-Semantics that allows you to transform RDF ontologies. So basically, these would be ontologies and taxonomies that might be stored in formats like OWL or RDF. And you can actually bring those directly into Neo4j and use those as a basis for building out your knowledge graph and using standard terms.
Oh, great. Thank you. Thanks for that explanation as well. Okay, moving on. Let's see. Okay, this is a great next question. Can the graph ingest near real-time status updates?
Yes, absolutely. So we have connectors. So for example, we have a Kafka connector that you can use to connect with any streaming platform. We generally advise that you don't bring in raw streams of IoT data into your graph. It's better to bring in things like alerts. So oftentimes we'll see customers, pre-processing their streaming data and basically creating topics that have temporal alerts in those. And then you can obviously bring those in near real time.
Awesome. Thank you so much for that. It looks like we have time for one more question. So let's do this one. How difficult is it to learn Neo4j?
Neo4j is really easy to learn. So any competent IT team that knows SQL can learn most of the Cypher language in just a day or two. You'll pick up the rest in a couple of weeks. It's a super accessible system. It's very intuitive. It's very flexible, and we have hundreds of partners that can actually help accelerate your journey into the graph if you want to use them as additional resources.
Thanks, Michael. And for those in the audience, thank you for attending. Have a great day.
All right. Thank you.